Hello all, in this video we will be stating and proving pumping lemma for CFLs. So the statement is like this: let L be any context free language, then there is a constant n depending only on L, the language, such that if Z is in L and Z is greater than or equal to this n, then we may write Z. We can split Z into 5 substrings U, V, W, X and Y such that we can meet all these conditions. That is Vx is greater than or equal to 1, Vwx is less than or equal to n, and for all I greater than or equal to 0, U, V raised to I, W, X raised to I, Y is in L. That means simply speaking there must be two short substrings V and X close to each other, which can be repeated the same number of times as often as we like. Okay, so that means this substrings V and X can be repeated. They are lying close together. They can be repeated same number of times as much as we want. So if we can meet all these conditions, the language is in CFL. Again, the application of pumping lemma for CFL is to prove that some languages are not CFLs. We don't use it to prove that a language is part of CFL, but we use it to prove that some languages are not CFLs. Okay, so in this video we will prove pumping lemma for CFL, and the next video will be proving that certain languages are not in CFL with the help of this pumping lemma. Okay. So this is, this is what we prove. That is, we have to prove that this is correct. All these three statements are correct of the languages in CFL. So that is what we need to prove. So for proving this, we will be using the help of parse trees, because you know that while we were using CFLs, we were generating the parse trees, isn't it? For example, of the languages like some T gives a C and A gives some B A and C gives some C A, and that of it is A is giving small a and B is giving small b. For languages like this, we'll be writing the parse trees like this. That is T, it gives A, it gives C. Now A is giving B, A is giving A. Now C is giving C, C is giving A. Now B can give B. This A can give, can give BA of it needs. Now this B can, BA or A. Now B can give B. This A can give A. Now this C can give C, A, C. Sorry, it is BA. Okay. Let's change this to BA to make this easy. BA. Now this B can give B. This A can give A. If it is like this, you know that the string or the word derived is getting by reading the leaf nodes from left to right. Example, BA is the word or string derived by this parse tree, isn't it? That is BA is the yield of this parse tree, or that is the word that was generated by this particular grammar here. Okay, that is we are reading the leaf nodes from left to right. All the leaf nodes will be having just terminals, and if you are reading the leaf nodes from left to right, we will be getting the word derived by this parse tree. Okay. So now we have to prove that all these conditions will be met. So to prove this, what we need to prove first, to get to this particular point, what we need to do is we have to prove that before that, you know that if some word Z is a word like BA. If Z is a word in a parse tree, you know that there will be a long path in the parse tree which can derive Z. If Z is really long word, you know that there will be long paths in the parse tree which can derive Z, right? That is, if Z is in language of G, then Z is long. If the word Z is long, then there will be a parse tree for Z, which will contain a really long path. Okay, now we need to prove that if the parse tree of G has no path greater than I, that is if the maximum path length of the maximum path length, then the path tree is I. Maximum path length. Okay, if it is I, we have to prove that maximum word length is 2 raised to I minus 1. So this is what we need to prove to come to this particular point. That is, if the maximum path length is I, maximum word length that can be derived from the tree is 2 raised to I minus 1. So let's just check with this tree before we move into the proof. Yeah. So here the maximum path length is 1, 2, 3, 4. Okay, 4 is the maximum path length. And the word derived is BBA. So the length of the word is 5. So it is much lesser than 2 raised to 4 minus 1, isn't it? 2 raised to 4 minus 1 is 2 raised to 3, which is 8. So the word derived by this tree is much less than the path maximum word length, which is 2 raised to 3, 8. So that is what we need to prove. This is what we want to prove. That is, if the maximum path length in a tree, maximum path length means the length of the longest path, that is obtained by counting the edges from root to the longest path's leaf node. Here these two are the longest paths, right? Yeah. So maximum word length, then of maximum path length is I, maximum word length will be 2 raised to I minus 1. So this is what we need to prove. So we will prove it using mathematical induction. So we will check the base case first. So in the base case, we will take I as 1, the path length as 1. For example, like the A giving A here, A gives A. So the path length is 1, isn't it? Just 1. So 2 raised to I minus 1 must be the maximum word length. 2 raised to I minus 1 is 2 raised to 0, which is 1. So the word length also is 1. So the path length is 1 and the maximum word length also is 1. So that is, if the maximum path length is I, the maximum word length is 2 raised to I minus 1. So that is met here. Okay. So that's our base case. Now we will take the assumption. Okay. So we will prove that, we will assume that for a particular path tree with edge length some I minus 1, some I minus 2, we will prove that if the maximum path length is I minus 2, we will prove that we will assume that maximum word length is 2 raised to I minus, I'm taking this I minus 1, yeah, 2 raised to I minus 2, right? So this is what we need to prove. So we can take that as an assumption. That is, we are proving that if the maximum up to the value I of the maximum path length is I minus 1, the maximum word length can be 2 raised to I minus 2. So this is our assumption. Now we will prove it using induction. Now we are, based on this assumption, we are taking a subtree T1 which is having the maximum path length I minus 1, and we are having another tree T2 which is also having path length I minus 1. So this will be having word length 2 raised to I minus 2, isn't it, according to the hypothesis. So this also will be having the word length 2 raised to I minus 2. Okay. Now if you are clubbing these two trees into a single tree, some T is branching to T1 and T2. Okay. You know that the path length will be, the path length also has increased by 1. Okay, here the path length has increased by 1. So the path length is I here. Here also the path length has increased by 1 because of this edge. So the path length has increased to I in both the sides. Now what about the maximum word length? So for getting the maximum word length, you have to count all the terminal symbols, right? So here we have 2 raised to I minus 2 leaf nodes here, and plus here also we have 2 raised to I minus 2 leaf nodes here. So the total leaf nodes are 2 raised to I minus 2 plus 2 raised to I minus 2. Is it? No. Yeah. What do you want? 2 raised to 2 plus 2 raised to 2 is actually 2 raised to 3. See, if you want to check, 2 raised to 2 is 4, 2 raised to 2 is 4, 2 raised to 4 plus 4 is 8, that is which is 2 raised to 3. So 2 raised to I minus 2 plus 2 raised to I minus 2 is actually 2 raised to I minus 1. So when the path length is I, because this contains path length I minus 1 plus this edge. So I is the total total path length. Here also the path length is I minus 1, with this path added the path length is I. So when the path length is I, we obtain that the total word length will be 2 raised to I minus 1 with the help of mathematical induction. Okay. So I will repeat this. In the base case, what we wanted to prove that if the maximum path length is I, the maximum word length will be 2 raised to I minus 1. So in the base case, we took I as 1. So we, for example, we took this tree wherein A is deriving small a. So when it contains one path, it is having just a word of length just one character. So 2 raised to I minus 1 is 2 raised to 0, which is 1. So when the path length is 1, the word length is 2 raised to 1 minus 1, which is correct in the base case. And in the assumption, we are taking that up to the values I of the path length is I minus 1, the word length will be 2 raised to I minus 2. So that is what our assumption is. Now we want to prove this for higher numbers than I. Okay, when the path length is more than I minus 1. So we are merging two subtrees of size path length, maximum path length I minus 1 and I minus 1, and we are merging them into a single tree using an edge connecting to the root node. So with this edge also connected, the path length of this subtree is I. This subtree also has the path length I now. Adding this edge also. Now to get the word length of the complete tree, taking left and right subtrees together, here the word length is 2 raised to I minus 2 and here the word length is 2 raised to I minus 2 according to the assumption. Now the total word length is 2 raised to I minus 2 plus 2 raised to I minus 2, which is 2 raised to I minus 1. Okay. So yeah. So hope that is clear. So this is how we get this. This is according to a suggestion, that is according to the this is what we wanted to prove, that is if the path length is maximum path length is I, the maximum word length will be 2 raised to I minus 1. So we could prove this using these 3 steps. So we have this theorem proof now, and with the help of this we will try to prove that all these 3 conditions can be met in a CFL. Okay. Yeah. So for this CFL, now what we will take is so we will take a grammar with some k variables. That is, the grammar is having some k non-terminals, and we are taking n as 2 raised to k. That is, we are taking this constant n as 2 raised to k, where k is the variables in the grammar. Okay, k is the variables in the grammar, and we are taking the size of input string as 2 raised to k. And we know that this is such that if z is in L, and the size of z should be greater than or equal to n, isn't it? So the length of z should be greater than or equal to n. N is 2 raised to k, isn't it? So length of z should be greater than or equal to k. That means z should be greater than 2 raised to k minus 1 for sure, isn't it? Z can be, because the minimum value z can have is 2 raised to k. Z should be definitely greater than 2 raised to k minus 1. That is, the minimum value allowed for z is 2 raised to k. The same thing. So we have written in this particular format. Okay. So if z is having length 2 raised to k minus 1, the minimum, then the tree should have at least k plus 1. The maximum path length should be k plus 1, isn't it? k should be the maximum path length. If k should be the maximum path length, that is if z is having the length 2 raised to k minus 1, k should be the maximum path length according to this theorem that we have just proved. The maximum path length should be k, then only the word z will be having length minimum of 2 raised to k minus 1. See, if there are path length is k, that means k plus 1 variables will be the variables or vertices. K plus 1 vertices will be there in a path. I will show you that. For example, this path length is 1, 2, 3, 4 because we are counting the edges. But this particular path contains 4 edges, then 5 vertices. 1, 2, 3, 4 and 5 vertices. 4 edges and 5 vertices, because in case of path length we are counting the edges, plus 1 will be the total number of vertices along that path. Hope you can verify from this. For example, the path length of this leftmost path is 1, 2, 3. It contains 4 vertices. So if the maximum path length is k, we will be having k plus 1 vertices. So hope that is clear. So we will be having k plus 1 vertices. But we have just k variables. But in a path we are having k plus 1 variables. So that means if the graph is originally having k variables, and if the grammar is originally having k variables, and if you are getting k plus 1 variables in a path, that means that one vertex is repeated. One vertex is repeated. Then only we will get this. One vertex is repeated. That means, one vertex in a path is repeated. One vertex is repeated in a path. So let V1 and V2 be these two vertices where V1 and V2 are having same label. For example, when we take this path, AA, both of them are having same labels, right? That is what it means. That is A and A. They are having the same labels. Like that. Let V1 and V2 be the vertices which are having V1 and V2 have same label. So in that case, one of them, say V1, will be closer to root, right? Because they are the same path. So one of them must be closer to root. So let V1 must be closer to root. Okay. And from V1, we can derive a tree, right? So from V1 also we will be having a subtree. We will be having a subtree rooted at V1. So V1 to root, not root, V1 to leaf will have at most k plus 1 vertices, isn't it? That is, we have k plus 1 vertices in the particular edge. If V1 is the root itself, we will be having at most k plus 1 vertices from V1 to the leaf node. Because even if V1 is the root node itself, very same root node itself, because this node can also be repeated. So if this is V1, that is the worst cases, and in that case also V1 to leaf node will be having maximum of k plus 1 vertices. So we have V1 and V2 with same label. So we say that the subtree T1 is rooted at V1 and the subtree T2 is rooted at V2. Okay. So this is how we represent it. That is, some subtree T1 is rooted at V1 and some other subtree T2 is rooted at V2. Okay. So like this, we will take this A as some V1 and we will take this A as some V2. Okay, we have more vertices repeated here, but still for the sake of the proof, we will consider the 2. Okay, because this just happened. So this is a subtree rooted at V1 and this is a subtree rooted at V2. So you know that if some Z1 is the yield of Z2 is the yield of T2, the subtree T2, some Z1, Z2 Z, or we can use Z3, Z2, Z4 is the yield of T1. Agreed? Because the yield of T1 will be some Z1 which is equal to Z3, Z2, Z4. Because Z2 is below Z1. Z2 is a subtree of Z1, or T2 is a subtree of T1. So T1 will be enclosing T2, right? That is T1, the yield of T1 will be some Z1 which is equal to Z3, Z2, Z4, where the yield of T2 is included, which is Z2. For example, the yield of the subtree V1 here is BA, isn't it? This is Z1. The yield of the subtree T2 here is BA. This BA is the yield of the subtree T2, which is Z2. That is yield of the subtree Z1 is some Z3, Z2 and some Z4. Either of them can be epsilon also. Here Z4 is epsilon. Z4 is actually epsilon. Z3 is actually the B. This particular B is a Z3. That is, either of them can be epsilon also. So this is how we write this. Okay. Now, so Z1 can be written as Z3, Z2, Z4. So if you look at this, you can see that this vertex label is A and this vertex label also is A. That means A is repeated. That is, A is recursive in it. Then only we will get the same vertices with the same label along a particular path, isn't it? That means some kind of recursion is there in it. So that means then only we are getting the same vertex along a path if and only if that particular variable is recursive in it. So that means we can repeat this particular Z3 and Z4 any number of times. That is, we can repeat this Z3 and Z4 any number of times. That is, Z3 and Z4 can be repeated any number of times. They will be repeating equal number of times because they are the yield of A1. So when A is repeated, this B and A will be repeated again and again, isn't it? So thus Z3 and Z4 can be repeated any number of times. Okay. Now if you are having if the tree is a little more bigger, that is, if we have T as the subtree or something, you may have other strings to the left of it and to the right of it. For example, if you have some U to the left of it, if you have some V to the right of it, you can write it at U to the left of it, and some Y to the right of it. You can write it as U, V, W, X, Y. Is in the language of Z. That is, here you can repeat V can be repeated, W, now X can be repeated, and then Y. So you can always write it in this format. And since the same labels appear along a particular path, as I told, that means the variable is recursive in itself. That can be repeated any number of times. So this V and X can be repeated any number of times. Okay. And then they should be repeated the same number of times. Either of them can be epsilon also, that doesn't matter. So this is again the part of this language, because since the variable is recursive, all the strings that are derived from the grammar by a repeated application of that variable is also in the language. So U, V raised to I, W, X raised to I, Y is also part of this language. So this also is a context-free language for any value of I. That is, you can repeat that any number of times. So that is how we prove pumping lemma for context-free language. So I'll repeat this. So this is pumping lemma for CFLs. That is, we can divide the string, the word we want to check whether it is part of the language or not, into 5 substrings U, V, W, X and Y, and the length of V and X combined together should be greater than or equal to 1, and V, W and X should be less than or equal to N, and for any I greater than or equal to 0, U, V raised to I, W, X raised to Y. For all I greater than or equal to 0, U, V raised to I, W, X raised to Y should be element of L. For proving this, we can take a tree and showing that the recursion in variables, we can say that some strings can be repeated. But again, to show the maximum word length, the relation between maximum word length that a tree can derive and maximum path length, to substantiate the proof, to help us in the proof, we needed to prove this particular theorem first. So we proved this theorem first, and then only we moved to the actual proof of pumping lemma for CFL. For proving pumping lemma for CFL, we took a grammar with k variables. Then we took the value of n as 2 raised to k. Then z is greater than or equal to n. That means z is strictly greater than 2 raised to k minus 1 here. Now the if it is 2 raised to k minus 1 is the maximum word length. The maximum path length is k. So maximum path length is k. But we know that in a path, if the path length is k, there will be k plus 1 vertices in that. But we have just k vertices in the original grammar. That means one vertex is repeated in a path. That is, in the same path from root to leaf, one vertex has been repeated. That means that particular variable is recursive. Then that means that variable is deriving itself in one or more steps. That means the variable is recursive in itself. So if the variable is recursive in itself, we can substitute that variable for itself any number of times and can increase the length of the string that we can derive. That means we can pump v and x any number of times. The only thing is that we should be pumped the same number of times as x. So since it is recursive. Okay, so to help this proof, we proved this first. That's all. So hope this is clear. This is how we prove pumping lemma for CFLs. Hope the proof is clear. In the next video, we will see examples for pumping lemma. Thank you.